With our analysis of compressibility and the ether equations of motion now complete, we can turn to using the prior equations in a derivation of Maxwell's equations. First, recall that our investigation concerning incompressibility of the ether led us to equations 4, which are presented again here. We can now derive Poisson's equation quite simply by subtracting these two equations. We form the Laplacian of psi sub p and subtract the Laplacian of psi sub n. We then apply the Laplacian to the difference and substitute in the relationships that are found in equation 4. Now we will let psi sub p minus psi sub n be equal to minus phi over 4 pi rho 0. This is the defining equation for phi. And we'll also define the rho sub d as rho sub dp minus rho sub dn. This leads us to the equation, by simply substituting in these values, of the Laplacian operating on minus phi over 4 pi rho 0 equals to rho sub d over rho 0. Or we can cancel out the rho 0 on each side of the equation and bring the minus 4 pi to the other side to arrive at the equation del squared phi equals minus 4 pi rho sub d. Now we'll move on in our analysis and recall equation 7 from a previous slide, which is the equation of motion for the attached positive ether. In order to simplify the mathematics, we'll define the vector J as the net current of detached ether that flows through the attached ether. J is the density of the detached positive ether times its velocity minus the density of the detached negative ether times its velocity. Recall from our review of vector calculus that it is always possible for any vector field to be divided into a transverse component that has zero divergence and a longitudinal component that has zero curl. We'll do some manipulations of the transverse expression a bit later, but for now we will start by manipulating the longitudinal expression. The first step is to notice that the longitudinal displacements can be represented as the gradient of a scalar, as was shown in our review of vector calculus. P sub L can be expressed as the gradient of psi sub p, and n sub L can be expressed as the gradient of psi sub n. We can then again make the substitution for phi as was made in the previous slide, shown again here, where phi divided by 4 pi rho 0 is equal to psi sub p minus psi sub n. As can be seen, making this substitution changes the sign on the second term of the right-hand side of the equation from a minus to a plus, and also cancels out the 4 pi rho 0 term. This leaves the longitudinal portion of the positive ether equation of motion in the simplified form shown here. Note that we have reversed the order of the gradient operation with respect to that of the partial differentiation with respect to time, but that such an action can be done with well-behaved functions. This slide begins where the previous slide left off, which is the longitudinal portion of the equation of motion for the attached positive ether. To manipulate this equation further, we first take note of the continuity equation, which is the partial derivative with respect to time of the density of the detached ether being set equal to the negative of the divergence of the current, which is equal to the negative of the divergence of the longitudinal portion of the current. We next recall equation 9, which is that the Laplacian operator applied to phi is equal to minus 4 pi times the density of the detached ether. If we now take the partial time derivative on each side of this equation, we will get the expression shown here. Next, we will take the divergence of the right-hand side of the top equation. By bringing the right-hand side down, here inside the square brackets, we will simply take the divergence of that part of the expression. Then we will move the divergence operator inside of the square brackets to get the form shown here. We'll now set the divergence of J sub L equal to minus the partial derivative of respect to the density with respect to time. The minus sign goes away. And we will set the partial derivative with respect to time of the Laplacian operator applied to phi equal to minus 4 pi times the partial derivative of the density with respect to time. Again, the sign switches and we get the 4 pi being brought down from this relationship. We now identify the fact that these two terms are identical, and so therefore the divergence of the right-hand side of the expression is equal to 0. Since by definition of the longitudinal component, the curl is also equal to 0, we saw in our review of vector calculus that we can therefore set the right-hand side equal to 0. That means that the two terms will be equal because of the minus sign here. Hence, we are able to arrive at equation 10, which sets these two terms equal to each other. We will use this relation next. We will now turn to some manipulations of the transverse portion of the positive ether equation of motion, the equation of which is shown here. First, we will recall the equations of motion for both the positive and the negative attached ether, which were derived in an earlier portion of this webinar as equations 7 and 8. Notice that the right-hand side of these equations are identical, and therefore the equation of motion for n satisfies the same equation of motion for p as far as the flow and tension forces are concerned. Next, note that the incompressibility relationship resulted in purely longitudinal separations of the ether. Therefore, the transverse portions of n and p are equal, and the second term in the starting equation can be set to 0, which is shown here. Next, from equation 10 on the previous slide, we had a relationship for the longitudinal portion of the current and the gradient of phi, such that we can add and subtract one term and the other from the initial expression, since we're essentially adding 0, since the two terms are the same. As a last step, we can combine the transverse and longitudinal current terms to arrive at the following expression, equation 11, which we will bring down to the next slide. It is now time to put everything together to see how the simple ethereal model proposed at the onset of this webinar has led us to a derivation of Maxwell's equations. First, we will recall equation 9 from the slide named Maxwell's Equations 1, which is reprinted here. Next, we will recall the final expression from the previous slide, which is shown here. We will then define the vector A to be equal to the n sub t or p sub t divided by little a squared to get the expression shown as equation 14. Also, we'll make note of the fact that the divergence of a transverse vector is equal to 0. Finally, we will recognize that equations 9, 14, and 15 are Maxwell's equations in the Coulomb gauge.